This section looks at the interaction of trees and fungi. So with every tree on Earth, there's an interaction of fungi with the roots of the trees. So these fungal threads that come off of the roots, they can go more than 1 kilometer out and 1.5 kilometers down. So they're really quite extensive, their reach. And these fungal roots, or threads, have acid tips on them. And they tend to break down mineral deposits from rocks that are really far away and bring them back to the tree. In order to do this, the fungi exchanges this for starch that comes from the tree. So the tree uses photosynthesis to create these starches to feed the fungi in exchange for these minerals that the fungi mines really far away. And some of these mined some of these mined minerals are phosphates. And in the course videos, I will put a link to a video that shows kind of groves of trees and how they interact with one another. So it's been shown in certain studies that when there was a large forest of trees, the important part here is that the trees do, in fact, interact with each other constantly. So when a swarm of insects came in and attacked one side of a forest, the other side of the forest started producing tannins, which repelled the insects from their leaves. And the only way that this possibly could have happened was from the fact that this tree, when it started to get attacked, through the root systems and these fungal networks, was able to communicate with trees further away and tell them, look, these insects are coming, we need to protect ourselves. And as a response mechanism, other parts of the forest were able to counteract this type of activity. So this communication crosses across the fungal network as a response to stress, and this communication is then transferred to other trees in every direction. And of course, since these fungal networks can go as far as 1 kilometer, they're going to be intersecting with other fungal networks from other trees, and this message is almost like a game of telephone where that message can just keep getting passed further and further and further along as well. Not only are these tree roots connected from these fungal networks, but very often the tree roots themselves will actually be connected from tree to tree within a forest as well. Sometimes even trees of different species will connect with one another. Nitrogen fixation can also take place in the trees that have bacterial associates. So when we were talking about things like the P and B family, so legume type plants, they have nitrogen fixing roots. So mostly trees with a pod are part of the legume family. Caraganas, peas, beans, vetch, and on their roots are partner colonies of rhizobia bacteria in legumes. So when we have a tree and we have the root system, and this would be a legume type of tree, it has nodes of bacteria on its root system. And with the legumes, this is rhizobium bacteria, and there are some other species of tree that also have these, and some non-legume plants that also have this similar kind of association happening with bacteria. Things like alders, bayberries, anything from the Oleaginae family, so the oleaster family, things like sea buckthorn and buffalo berries, autumn olives. And instead of rhizobium bacteria, they interact with the Frankia bacteria, but it's a very similar exchange where, again, the bacteria, like the fungi, are getting starch from the tree in exchange for providing nitrogen to the tree. And this tree then acts as a pump as well. So the hierarchy of the nitrogen in trees, when we're looking at what parts of the tree have the most nitrogen, the seed has the most nitrogen, followed by the pods, the leaves, the twigs, and then the wood, which doesn't have a lot of nitrogen in comparison to the other components. But when all of these elements break down, so the seeds, pods, leaves, twigs, and wood, when they all break down over time, when we use them as mulch, or if the tree just dies back, or if things fall off in the wintertime, or in the fall, then they release a bunch of this nitrogen back into the soil. So this energy transaction is a major fertilizing event in our systems. When the tree dies back, there's no longer any starch being made. So what happens is the nitrogen and the bacteria are released back into the soil, where the bacteria then dies because it doesn't have its food source of the starch anymore. And then those bacteria become food for other bacteria, which die off and become food for other bacteria. And this effect can be quite long-reaching. So these bacteria in the soil are 90% nitrogen. If they existed on their own in the soil without being connected to these roots, they are so microscopic and so tiny that they would just wash right through our soil structure and more or less disappear. They really do need to be latched onto something. And so the bacteria actually uses the starch from the trees not only as a food source, but also to make a gel that kind of helps them all stick together. And this gel is what forms the crumb structure of our soil. And that crumb structure is the very best structure for soil because it allows air and water to freely move through the soil. And when that crumb structure is present, then we know that there's a reasonable amount of beneficial bacteria and nitrogen in the soil for our plants. So these bacteria become stable when they're connected to the roots. They often look like nodes. Like if you pull the roots right out of the ground, you'll see actual pea-size to potato-size nodes on the roots of the plant. And then when they're not connected to the roots, they become that food for the other bacteria again, and they tend to migrate away from that zone. So there's a way that we can speed up this system because we want this to happen a lot quicker than it normally just happens in nature. Because in nature, we typically have to wait for that once a year opportunity when the leaves will fall in the fall in a temperate climate. And we want this whole system, and we want that nitrogen to be released into the soil for other plants much quicker. Because although this nitrogen is available for these particular plants, these legumes and these alders and things like that, we want that nitrogen available to our fruit trees and to our other plants. So the way that we speed this up is we can go ahead and cut some of the tops off of these trees. And when we do that, then the tree can't pump anymore and it seals off its roots in order... I have no idea why that's not working suddenly. And it seals off its roots in proportion to how much of the top of the tree is cut off. Then the bacteria that's down below here tends to get cut off from its starch supply. And then that nitrogen is released into the soil. And you can also use this material that you've chopped off as a mulch material somewhere else, where as we saw, the seeds and the leaves and the twigs are very high in nitrogen and can be used as a mulch for other plants. So what we've done when we chop off the top of a tree, or parts of the top of a nitrogen fixing tree, is we have sped up a time event. So we can very often do this with these plants even several times a year. Things like caraganas, for example, in the prairies, they regrow very, very quickly. And they, when you speed up these time events, and if you stack these and you do a lot of them and you speed up their succession over and over and over again, then you're essentially speeding up the growth of an entire forest. When you put the top of that tree back down onto the ground, the nitrogen is feeding other trees, and the wood itself is also feeding the fungi. So fungi is necessary to break down the lignin fiber in the wood. So the forest acts like a very complicated organism at this point. You can create an incredibly stable forest system. It's long-term and you can speed up these cycles, but it's also very vulnerable to people who just want to cut these trees down. So I like to think of this as a bit of like a zombie apocalypse type situation. When we have an annual garden, if you think about if the world comes to an end and people are scrambling around looking for food and they come across your annual garden, they are going to wipe the entire thing out, steal all the produce, and that poses a problem because then they've not only eaten your food supply, but they have also consumed or taken the seeds that you need to be able to restart that crop the following year. So they could leave you without food or the seeds to start fresh. And again, if somebody comes in and sees that you have a herd of cattle, well, there's a whole bunch of free beef for them, and they might kill them for food, and then you might not have enough breeding stock left to replenish your supply. But if you have a food forest, first of all, most people won't even recognize that it is a food source because it's going to be so diversified and just look like a forest. But also, not all the food is going to be ripe at the same time. So even if they come in and see, ooh, look at all the Saskatoon berries, they are going to eat the Saskatoon berries. But the tree still remains, the bush still remains to produce the Saskatoons the following year. And maybe 2 weeks later, suddenly there's chokecherries. And then maybe a couple months later, there's suddenly hazelnuts. And so no one can just come in and wipe you out of the whole thing. And it's also not going to, so it's not only going to be not fruiting all at the same time, but also if you're starving and you're looking for food, you're not likely to just start chopping down a bunch of trees or digging up trees to try and steal it because you're going to be trying to conserve your energy. So the food forest is definitely worth protecting because it's long-term and it's sustainable. It's improving the climate, and it's also producing a surplus of carbon for us.